Welcome to Chapter 5 of this course on partial differential equations. Today we will discuss the finite element method, or FEM if you are a close friend. As you know, solving a partial differential equation explicitly is often difficult or impossible to do. Most often you can't find u of the variables equals something. That's not happening. So you have to find an approximation of this solution. The finite element method is a numerical method that would exactly allow you to do this. And it is based on several ingredients. The first ingredient is the versional formulation of the PDE, which is what we discussed in Chapter 4 last week. The second ingredient is the discretization of the domain, and we're going to discuss this today in Section 1. It's also based on replacing the partial differential equation by its discrete counterpart. Basically, we will see what is the value of the solution, the unknown solution, at points that are the nodes of that mesh. We're going to explain this to you in a few minutes. And then we'll have to solve the discretized problem, and that will basically lead to us solving a linear system of equations. Before we start, let me actually give you a few elements of history of the finite element method. And in the 1940s, we have Enrikov and Courant, who developed a mesh discretization method that was used, especially for mechanics problem, basically civil engineering, aeronautical engineering, and that was in the 1940s. In the 1950s, the first paper was published, and actually we have a series of papers published by Argyris under the title Energy Theorems and Structural Analysis that developed quite a few elements of linear algebra that are useful for the finite element methods. Then IBM and General Motors built the DAC-1, which is a computer system that was used to develop cars using the finite element method. In the 1960s, the term finite elements was actually coined by Clough, and Zankiewicz published the first book on the finite element method. Then,
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the earth.
And NASA developed Nastran, a solver tool for structural analysis problems. Since the 1970s, there has been a very strong development of finite element methods and industrial use in simulation. In France, Jacques Williams has promoted the finite element method, and there were a lot of papers, very high quality papers on the method. A tremendous number of results have been published. The finite element method has expanded rapidly for two reasons. Number one, the mathematical tools became available. And number two, the computing power is also, extremely impressive. I mean, as you know, it doubles every 18 months as the Moore's law, and you need to realize that your phone has more computing power than the entire Apollo program altogether. Okay? And what do you do with it? You watch videos of cats. Okay, we have this computing power, we have the method, so obviously the finite element method has expanded rapidly. Today, it is widely used for numerical approximations of PDEs, which themselves are widely used for simulating reality. And I would like to point out that in 2004, the Falcon 7X became the very first aircraft in history to be entirely developed in a virtual environment. So basically it was completely developed, and then we actually start with the prototype, and then basically that prototypes takes off. Everything was done numerically. There are still many challenges though. First, multi-physics, coupling. I mean, we have very many phenomenon working together. That means that basically we have partial differential equations that are coupled, which means that one solution to one is a parameter to the other one. So it can be complicated. It's a multi-physics. Also multi-scale, which means that we might have several phenomena that actually interact at different scales, and that is also something which is a challenge. We have complex systems and the interactions within the systems. We need robust solvers. We obviously still need to work on computing time, especially if you want to work real time. That's obviously a challenge. And each and every graduate from Central Supélec must understand how to use the finite element methods and also what is the underlying foundation of finite element method. This is why we're going to work together in this chapter to make sure that you understand how it works. And at the end of the chapter, we'll also see a few numerical software and libraries that you can use, so you don't have to do everything by hands all the time, of course. And we'll actually, we'll use in this class, in this course, Phoenix to actually simulate solutions to PDEs. Before I give you the outline of this chapter, I would like to give you a few examples of what you can do with finite element methods. This obviously is a plane, and you can actually compute some of the properties of what's going on with this plane based on, using finite element method. This is a diffraction which is completely done numerically. That is something that you can also do. In terms of medicine and biology, here is some arteries, and obviously some of the diseases that actually can be a problem, and you can actually simulate what's going on in terms of what's going on with this artery here. Here is a dolphin that is swimming in the water, and you want to see the interaction between the skin of the dolphin and the water, depending on the angle and also the speed of that dolphin. Here is what happens. Basically, it is a simulation of a crash, and as you know, in the car industry, you need to have your car, you need to test your car for crashes, so you want to protect people inside the car, so you need to see how things go. And before you actually put a dummy in the car, you may want to run a few simulations so you can reduce the number of crash tests you do, which obviously take time, they take money. And so if you can actually reduce this, then it's good for everybody. You can increase the safety of your car, decrease your cost, which you can eventually pass on to the customer, so your car will be cheaper. Everybody wins. The car is cheaper, the manufacturer is happy, you save life, and the mathematicians can actually develop some good contract with these companies and actually finance some postdocs and PhD students, as well as going to conferences. So it's a win-win-win-win situation. And I wanted to show you a simulation that is made by ANSYS on basically facial masks. These are N95 masks, and you can actually simulate what is going on depending on whether it is properly fitted or not. So here is the outline of this chapter. We're starting with this introduction, after which we will have two videos on section 1. The first video will be on mesh. We'll generate a mesh, and the second video will be on the internal approximation. After this, we will put together the finite element method. So first, I will give you the outline of the method, then we'll do that in dimension 1, and then in dimension 2. And after that, we'll discuss some finite element method software and libraries. I will give you a non-exhaustive list, and I will give you a few examples using the Phoenix library.